After some technical difficulties that Barnabas solved for us. So your homework is due today, just to remind you of that. Turn it in before midnight on Blackboard. I think last time there was some problems with people submitting it. Maybe it was the Blackboard system was a little bit funky or something. So make sure you give it a try earlier than midnight this time in case you have problems. Give yourself some buffer. Are there any questions about homework submission or anything like that, besides homework content, which we can't really talk about now? Okay, so we just finished up first and second order methods. That was the last, I don't know, maybe something like 8 lectures we talked about. And today we're talking about duality. And we're going to move into duality and the KKT conditions for the next couple lectures. Before we leave the algorithms world, we'll come back to it in a little bit. We just put together this table that's it gives you kind of a crude summary of some of the methods we've learned and their properties. And we're going to keep adding to this as we learn more methods. And then we're actually going to spend an entire lecture. The lecture title is called Putting Things Together, where we talk about, in different problems, what kind of properties of the problem would guide you to use one algorithm over another. So here's a summary of what we've seen so far. And you can make sure that the entries of this table make sense to you, but we can just go through it quickly now. So gradient descent, it uses a smooth criterion, right? Subgradient method is any criterion. So kind of, I didn't write this on the slide, but f is convex here. We're assuming that all these functions are convex. In addition to that, what are we assuming? For gradient descent, it's smoothness. For subgradient, there's no smoothness assumptions, right? Just convexity. For proximal gradient, or generalized gradient descent, it's that we have a smooth plus a simple function. The simple function could be non-smooth. For Newton, it's doubly smooth. So we need actually 2 derivatives of that function. The same is true for conjugate gradient and for quasi-Newton. Like the BFGS and the, was it DFP? Is that the DFP methods? How about constraints? What can we do with constraints for these methods? Well, we can do gradient descent if we can project. If we can project onto the constraint set, then we can take a projected gradient step, right? Same with subgradients. So any kind of constraint set that we know how to project onto, we can handle with these methods. How about generalized gradient? This is actually a little bit tricky. How about if we have minimize f, which is g plus h, subject to x and c. How do we do that with proximal gradient descent or generalized gradient descent? Thoughts?
You add the indicator function.
Right. That's kind of like our standard trick. There's not much else we've done. So we add this indicator function. And now what's the decomposition into smooth and non-smooth? Yeah, this guy is like our new h, right? Maybe like h tilde of x. So what's the proximal operator? So the generalized gradient descent repeats the following steps. It takes the prox of h tilde in t of x minus t times the gradient step. So what is that? That's the argmin over all x, or maybe I should call it another variable, over all, say, z, of 1 over 2t times x minus t times the gradient minus z squared plus h tilde of x of z. All right, so then let's just expand back out h tilde. That's the argmin over all z in c of 1 over 2t, this whole same bunch, minus z plus h of z. So actually, we're solving a constrained proximal operator problem, right? Because we have this constraint here. Is really what it comes down to. So even if h was simple, like remember the L1 norm, we knew how to do that. That was just soft thresholding. Once we add this constraint set, this could actually become challenging again. So generalized gradient descent, if we want to minimize g plus h subject to constraints, that could be challenging. Like this could be a challenging proximal operator to figure out, even if the proximal operator of h was simple. So that's why I wrote constrained prox operator here. How about Newton's method? Well, for Newton's method, we talked about it unconstrained. But actually, if you have equality constraints, there's a very kind of natural way to extend Newton's method to handle those equality constraints. Like if I want to minimize f of x subject to ax equals b with Newton's method. And it just comes from basically when you solve a linear system in Newton's method, right, we solve this linear system that involves the Hessian at each step. We also add into that linear system that the direction we take a step in should preserve this linear constraint. So it's actually like solving a larger set of linear systems. And yeah. Yes. So you can take a look at the formulation for that in the textbook that you have, but that's just basically the idea. Conjugate gradient and quasi-Newton methods, we talk about them unconstrained. We'll talk about how to handle constraints for any of these methods, Newton's method, conjugate gradient, and quasi-Newton, in a more general way when we talk about interior point methods. We use what are called barrier functions. So then we'll have more stuff to add to this table later. How about step size choices? Well, gradient, remember, we could use t, which is less than or equal to 1 over the Lipschitz constant. We knew that converged. Or we could use backtracking. Those are the two options we talked about. Subgradient, remember, we didn't have any analogy to backtracking. And there was no fixed rule that would really work for us. It was rather, if we took step sizes that were diminishing, that went to 0 fast enough, then that would work for us. Proximal gradient's the same step size ideas as gradient descent, except for the Lipschitz constant here is just the Lipschitz constant of g, the smooth part. We talked about pure Newton's method, which is Newton's method without any kind of choice of step size, just taking a step size of length 1. And that's kind of the most classical approach to Newton's method. That can diverge, and we talked about that. So then backtracking is a common thing that people do in Newton's method as well. It's just the same formulation as you do, say, in gradient descent. The step size rules got a little more complicated for conjugate gradient and quasi-Newton methods, but we had them in the slides. Right? We had different ways of choosing step sizes depending on which variant of the method we were using. And then here are the most practically important two items. I mean, they're all important. I guess I shouldn't say the most. But how about the iterations? Well, iterations of gradient descent, remember, they are very cheap. They just involve computing the gradient. That's all we're doing. Same with subgradient method. We're just computing a subgradient. And for the proximal gradient descent, they involve one evaluation of the prox operator. So I put moderately cheap because, depending on what the prox operator is, that could be cheap or it could be kind of expensive. The expensive example we had was when the h part was the nuclear norm. So the prox operator required computing an SVD. But there are cheap proxies as well, like for the L1 norm. Now we're on Newton's method. Moderate to expensive. So what do we need to do? We need to compute the Hessian and solve a linear system in the Hessian at every step. Right? That's what the Newton step was. It was taking a step in the direction of the Hessian inverse the gradient. So this could be pretty efficient or moderately efficient if the Hessian has structure. Right? Because in that case, we're solving a structured linear system, like a banded matrix, for example. But it could be pretty expensive if the Hessian was arbitrary. So it depends really on the problem's details. Now, what about the conjugate gradient and quasi-Newton methods? Well, I put moderately cheap. If you look at what the steps are, they involve computing gradients and inner products, basically, for conjugate gradient. Right? There's no matrix inversion. And that was also true of the quasi-Newton methods. In fact, that was really the main motivation for them, was that we got away without having to invert the Hessian because we were estimating the inverse Hessian in kind of a clever way. But Barnabas made the good point that we still need to store the estimated inverse Hessian. Even if we're not actually computing it, we need to store it. And if you have a really big problem, that's storing p-squared things. That could be itself somewhat of a limitation. And then how about the rates? So this is how fast each iteration is. This is how many iterations that we expect it to take to converge. So these things together tell us about the speed of the algorithm. For gradient method, or gradient descent, we had different rates for different assumptions. So the standard rate is 1 over epsilon, if you want to be within epsilon of the optimal criterion value. That's how many iterations we need to get to within that accuracy. That's if we assume that the function is Lipschitz. I'm sorry, if the function's gradient is Lipschitz. If we use acceleration, which we didn't cover in class, but the optional exercise in the homework is to, one of the optional exercises on this homework is to implement it. That brings the rate down to 1 over the square root of epsilon, which is a pretty nice improvement. And if the function is strongly convex, then actually that's a very smooth function. We do well with gradient descent. We get log of 1 over epsilon. So this is linear convergence. That's what the log of 1 over epsilon is called. How about subgradient method? Well, it's a lot slower. It's 1 over epsilon squared. So it's an entire magnitude of efficiency slower than gradient descent. And we saw some examples of that where we actually plotted the functions, the value of the function we're trying to minimize with respect to the number of iterations. And we saw that those curves look really different for subgradient method and, say, gradient-based method. For proximal gradient, it's the exact same story. It's all the same rates. The assumptions are just now made about g, the smooth part, assuming we can actually evaluate the prox operator. Newton's method now brings us to a whole other regime of speed. It's not only better than gradient descent in kind of the case where we assume the most strong assumption, strong convexity. It's even faster than that. It's log of 1 over epsilon. So this is called a quadratic rate. So just stick in some values of epsilon and stick in smaller and smaller values of epsilon and look at how these things scale. You'll see these are actually very different rates. But remember, this has to do with number of iterations, and each iteration of Newton's method is much more expensive than an iteration of gradient descent. Right, so like I said, it's really these two rows together that tell you the speed of the algorithm. For the last two quasi-Newton methods and for conjugate gradient methods, we didn't talk about the rates that explicitly. And so I had Barnabas fill this section out here. And I think we didn't write down a specific rate in terms of epsilon because it would be a little bit misleading. But the thing to remember is that if you take n steps of conjugate gradient or n steps of one of these quasi-Newton methods, that's like equivalent to 1 Newton step. So it's an n-step quadratic rate. If you take n steps under some assumptions, you should expect to achieve the same decrease in the criterion value as you would with 1 Newton step. Was that kind of a fair way of summarizing?
Another note that these rates are local rates only, so you have to be close enough to the minimum to get these rates. If you are far, then anything can happen.
Okay. Any other questions about the summary slide? Okay, so like I said, we'll return to this kind of stuff in a little bit with more information and more methods to talk about, but something to hold on to at this point. So duality is what we're talking about today. We're going to start off with duality in linear programs because it's really I think it's the simplest way to introduce duality, and it has a very nice concrete construction in this case. It's also historically, it's the problem in which people first started thinking about duality. Duality for linear programs came before the general construction for duality that we have now. So let's just suppose we had the following goal, and then why we are trying to achieve this goal is going to become clear as we talk more and more about duality and the KKT conditions. But let's just suppose we had some problem, minimize f of x over some constraint set x and c, and we wanted to lower bound the optimal value. We wanted to find some value b that was smaller than or equal to the optimal value of our program. So that's our goal for now. It's not necessarily easy to see how to do that outright unless we are in some very special circumstance, like we knew f was always positive or something. So in particular, we're going to talk about LPs. And right, so let's suppose we had the following LP. So I'm going to minimize x and y are now just real valued over x and y. The objective function x plus y subject to x plus y is bigger than or equal to 2. And x and y are bigger than or equal to 0. So what's the lower bound for that LP, for the optimal value of this linear program? 2, right? So we didn't have to do anything. It was kind of silly. One of the constraints just gave us that the optimal value is lower bounded by 2. No matter how we try to solve this, we know it has to be the case because it's written into the constraint set. So that was kind of easy. And maybe you think, well, we just got lucky because I wrote down this linear program, and that's not a very general strategy. So let's try to do it again, but with a little bit more complicated an example. Let's suppose now we had minimize x plus 3y subject to the following constraints. Again, we have x plus y is bigger than or equal to 2, and x and y are non-negative. So any ideas for how we could try to construct a lower bound for our objective function at its optimum? Yeah, that's a good idea. So I'll write them all out. So what would I do? Okay, but so what specifically would I do in this example? That's the right strategy, but let's just think concretely. What's that? I want to somehow take linear combinations of these constraints in a way that it gives my objective function. That was the thought. All right, so what happens if I multiply this by 2, for example? That's still a legitimate constraint. If y is bigger than or equal to 0, that's the same thing as saying 2y is bigger than or equal to 0. And now I can generate a new constraint by adding the first and third together. That tells me that x plus 3y is bigger than or equal to 2. So now, actually, look, I've made this by construction the same as my objective function. So I can just read off that, again, I can take b equals 2. That's the lower bound for our objective. So let's do this, but with an objective function that takes an arbitrary form, and we'll see if we can spot a pattern. So if I have px plus qy, and I have the same constraints, say x plus y is bigger than or equal to 2, x is bigger than or equal to 0, and y is bigger than or equal to 0, what would I do here? So it's not going to make sense to multiply by a number because these are arbitrary. But I'll introduce variables, a, b, and c. And I'm going to make them all non-negative. Because if they're not, then I can't really multiply them by any of these constraints because it would change the sign of the constraint. So that wouldn't be legitimate anymore. But I can multiply now c by this constraint, b by this one, and a by this one, and add them together to make any new constraint that I want that's a legitimate constraint. So I can say ax plus ay plus bx plus cy is certainly going to be bigger than or equal to 2a. That came from the first constraint. Right? And then plus nothing, because I have b times 0 and c times 0. So this is the lower bound for this quantity. 2a is always smaller than or equal to this quantity, as long as x and y are feasible for this linear program. That's all we've said. If x and y are feasible for this linear program, then 2a lower bounds that quantity. Now what do we want to do? we just want to make this quantity equal to our objective function. So we want to choose a, b, and c so that this is the same as px plus qy. So let's just collect the terms multiplying x first. We get a plus b times x plus a plus c times y is bigger than or equal to 2a. And as long as I make a plus b equal to p and a plus c equal to q, then I've lower bounded my objective function. So let's just write it out. So we have lower bounds is given by any a, b, and c bigger than or equal to 0. So the lower bound is it's equal to 2a for any a, b, and c that are non-negative and that satisfy a plus b equals p and a plus c equals q. Nod your heads if that made sense, because this is a kind of the fundamental point for duality. Are there questions about this? Yeah.
There are three variables, but only two equations, right? So can you always make a 0 to minimize the lower bound?
Yeah, right. But you're thinking ahead, which is good, because that's what we'll do in the next slide. Okay, so we've constructed a family of lower bounds now for this problem. Right? Any a, b, and c that satisfy this. If we take 2a, it's a lower bound. And in particular, we're going to want the tightest lower bound possible. We're going to want to make the lower bound as big as possible because that's going to be the most informative in some sense. So we can write down the best lower bound, which is the following. Max 2a subject to a plus b equals p and a plus c equals q, and a, b, and c are positive. So what is this with respect to the original problem? Okay, so that was the better answer, but what type of problem is this? Yeah, but what class of convex optimization problem is this? It's a linear program. Okay. So there's too many answers to the questions I was asking, so that's my fault. But it's a linear program, right? So we had a linear program, and we wanted to find the best, the largest lower bound we could on its optimal criterion value. And we do that by solving another linear program. Right, so that's a kind of an interesting relationship between linear programs, is that any feasible a, b, and c give us a lower bound for this. But if we maximize over all a, b, and c the quantity 2a, we get the best lower bound. So this is called the primal LP. It's the original LP. And we call this, as you guys were guessing, the dual LP. It's dual. So what do we know in particular about the optimal criterion value for this LP with respect to the primal? The relationship in terms of the size of those two optimal values. What's that? Exactly. So we know that this has to be less than or equal to this optimal value. That was true for any a, b, and c. So it certainly has to be true for the maximum. So at least this gives us a lower bound for the optimal value here. It could be equal to, right? At this point, we don't know that. How many people think that it is equal to the optimal value? In all circumstances. Let's say in all circumstances. And how many people think that in some circumstances, if I take p and q and to be weird, it could be not equal? Okay, so we're kind of split. But we'll answer that question specifically by the time we get to the end of the lecture. All right, so we're going to try another one just because practice is helpful. Now I have minimum px plus qy subject to x being non-negative, y being less than or equal to 1, and 3x plus y is equal to 2. And I want to construct a lower bound for the objective. So I go through the same set of steps. I'm going to look at a variable a. I'll look at a variable b. But before I do that, I'm going to rewrite this constraint in the following way. Minus y is bigger than or equal to minus 1. That way I can make b positive or non-negative and multiply against it by minus y. And I have all these inequalities going in the same direction. And I have c. Do I need to make c non-negative here? I don't, right? Because no matter what c is, if I multiply both sides of the equation by c, it's still going to be an equality. I don't have to be worried about flipping the sign of one of a constraint or something like that. So c is unconstrained. C can be anything, positive or negative. So that means that for any a, b, and c of this form, if x and y are feasible for the program, I can take ax and I can take b times minus y, so minus by, and I can take c times 3x plus y, and that's going to be bigger than or equal to a times 0, so nothing, plus b times minus 1, so minus b, plus c times 2. Right, so this is actually equal to 2c, even though this was only bigger than or equal to minus b. But we kind of collapse that just by writing like that. Okay, so again, let's collect terms on x. So I get a plus 3c times x, and I get minus b plus 3c times y is bigger than or equal to minus b plus 2c. I made a mistake. Yeah, there's no c in here. No. What? Thank you. I heard a lot of comments about the y being wrong and the c being wrong, but when everyone says something, it's kind of hard to figure out what's wrong. But thank you for catching that. Okay, so we have p and q is what the target are for those two things. We want to make those equal. So in other words, the lower bound is minus b plus 2c, and that's a valid lower bound for any a, b, and c that satisfy a plus 3c equal p, and minus b plus c equals q, and a and b are non-negative, and there's no constraint on c.
What is you cannot formulate p and q using the constraints in this way? For example, the objective is x plus 3y, and the constraint is x plus y larger than 1.
I didn't understand the question specifically, but let me just write max down here and quickly just point out that we're going to maximize that lower bound, which is our dual construction. Say it again.
I mean, what if the objective is x plus 3y?
Yeah.
And the constraint is x plus y larger or equal to 1. So in this case, you cannot find any a and b to formulate the problem.
Yeah, so when we do LPs in general form, I think you'll see where what you're talking about comes into play. But
But in this case, you have to have x and y like greater or equal than something. You have to have like boundary for x and y.
not necessarily. I mean, that's just
Then how can we yeah, then plot this today.
what's that? Yeah, that's true.
Yeah,
So
all these terms
So sometimes the dual or the primal can be infeasible. And you'll see kind of in the most general form, when we talk about general form LPs, what's going to happen. I think that'll be kind of the best way to answer it, because going case by case might seem like there are confusing, peculiar cases. But there are really only a few cases that you have to think about when you take LP duals. So here's a general form LP. And we're going to go through the same construction and get a general form dual LP. Okay, and you'll probably actually have the answer to your question just in a moment. So let's suppose that our LP is minimized C transpose X subject to some equality constraints and some inequality constraints. And this captures everything we would want to express in an LP. And I claim this is the dual LP right here. Maximize over a new set of variables, U and V, minus B transpose U minus H transpose V, subject to this equality constraint, minus A transpose U minus G transpose V is C, and just a non-negative constraint on V, no constraints on U. So this is an LP, that's also an LP in the most general form. And let's just go through that derivation. So we had minimize C transpose X subject to AX equals B, and GX is less than or equal to H. So I took U here and V here, and so this is a set, say, of M constraints, and this is a set of, I call it R constraints. So that means that U and V are actually going to be vectors, and I'm going to multiply, say, the ith component of this equality constraint by UI. So as long as V is component-wise non-negative, if I take V transpose AX minus B, and I add to that U transpose GX minus H, but I know this has to be bigger than or equal to, less than or equal to, wait, I multiplied V by the equality constraints, that was confusing. I have U transpose A minus B, and I have V transpose GX minus H. This is less than or equal to 0. Right, because this thing is positive in each component, and this thing is negative in each component. Or really, it's bigger than or equal to 0 and less than or equal to 0 in each component. So as long as V is non-negative and X is feasible, I get this equality, or inequality. And now I'm going to rearrange terms just like I was doing in the small two-dimensional LPs, and I'll get that the coefficient of X is A transpose U plus G transpose V, and I get that I can move that over to the other side, so I'll put a negative there, and I'll get that that's bigger than or equal to minus B transpose U minus V transpose H, H transpose V. See if I made any mistakes. Right. Thank you. So it's this times X.
And the parentheses is transposed?
Thanks. Okay, so I just rearranged terms and then took the X to the other side. In order to get a lower bound on our criterion, we want to make this equal to C. So that's exactly what this problem is describing. It says that this is a lower bound for any value of C, or for any values of V that's non-negative, and U can be anything. And to get the tightest lower bound possible, we'll maximize overall values of U and V that satisfy u can be anything, v can be non-negative, and u and v have to satisfy minus A transpose u minus G transpose v is equal to C. That's just exactly what we have here for the dual LP. So what happens now if, oh, I didn't have this written down. So your question was, what happens if I can't find u and v to add up to give me C, right? So the answer is going to be that the bound we get is minus infinity. But actually, the easiest way to see that is to look at the more conventional construction of the dual, which we'll talk about in a second. So maybe we can do that, and then we can, if you have questions still, we can come back to this version. Because this was really just a way to motivate how to construct duals in general, just for LPs. But the easiest way to see the answer to that question is once we talk about kind of like the general framework for duality. So we're just going to say a few things about LPs. So max flow and min cut. How many people have studied these problems in another class before? I guess quite a lot, since we have a good CS cohort. So Barnabas probably knows more about the history than me, so I might embarrass myself trying to describe the history here. But I believe that when people started working on max flow, they didn't know that the dual was min cut. Those are actually things that they didn't know. And people were solving both problems without knowing that they were actually duals of each other. So this paper gives a nice history of that, of the max flow min cut problem. But what is max flow? So max flow can be written as a linear program. And the idea is that we label, say, two nodes in a directed graph as S and T. And we're going to define something called a flow from S to T that satisfies some constraints, and those constraints end up being linear, so it ends up being a linear program. But a flow is anything that I assign to the edges in this directed graph that satisfies the following properties. If I am traversing the edge from I to j in this directed graph, then I have to make the flow non-negative. I can't think about going against the direction of that edge. And we also have for each edge a capacity of that edge. That's some fixed quantity that we predetermine ahead of time or that was given to us, and that's Cij. So there's this constraint that the flow we have on that we're going to be sending through that edge has to be less than or equal to Cij. And then this constraint is just very natural. It says that if I look at the flow coming into any one of the nodes in my graph, it has to be the same as the flow leaving that node as well. Right? So this is usually called conservation of flow. And that's true anywhere except for S and T, which are kind of like the endpoints of this flow that we're going to be sending through the graph, usually called the source and the sink. So we can formulate finding a flow, f, with these constraints that maximizes the value of the flow from S to T as a linear program. So we actually just want to maximize the flow leaving S, because by conservation of flows, that's just going to be the same flow that we're sending into T, because for any one of the interior nodes, the incoming flow and the outcoming flow are the same. Okay, so this is an LP. And we can go through the calculations for deriving its dual, which I'm not going to go through because we don't have that much time. But it's really just the same as what we've been doing before. And we introduce constraints for each one of these, variables for each one of these constraints. Right? This guy is unconstrained, so the variable for this equality constraint is unconstrained, and then we have a sign constraint for the variables for each one of these two constraints. And now, because it's an LP that has this maximize something, we're actually looking for an upper bound, and we're looking to minimize that upper bound over all choices of upper bounds. It's the same thing. In fact, we could have just written this as minimize the minus something and gone through our regular routine, but you can think about it either way. And what you get out of that is the following problem after you do all that. And if you look at this problem carefully, it ends up being the LP relaxation of what's called the min-cut problem. So we want to find a cut in the graph that minimizes essentially the capacities across edges that are in one part of the cut and the other part of the cut. So the min-cut problem itself is not a convex problem because we actually have these binary constraints, but if we relax it, we get this relaxed min-cut problem. That ended up being the dual problem of the max flow problem. So what we learn from what we already know is that the value of the max flow problem, by construction, we've upper bounded it by the value of our LP relaxed min-cut, just because that was the way we constructed the dual problem. And because it's a relaxation, it's going to have an even lower optimum value than the original min-cut problem, because we've just made its constraint space larger. Instead of having binary constraints for the variables, we made them between 0 and 1, so it can only get better. So we have this sequence of inequalities here. And there's this famous result called the max flow min-cut theorem, which tells us that actually not only is the value of the max flow equal to the optimal value of the LP relaxed min-cut problem, it's also equal to the value of the min-cut problem, this non-convex problem. So actually, these are all equalities. And moreover, what we're going to learn when we talk more about duality is that we can get the solution to one problem from solutions of the other. So they're all equivalent in terms of solving them. Not only are the optimal criterions equal, we can actually characterize solutions of one in terms of solutions of the other. So this was a very big find for people who worked in the field, in either field, max flow and min-cut. And so the question we're going to ask is, how often does this kind of thing happen? Was that just, we just get lucky with max flow and min-cut, or with the LPs I wrote down? Or do we always get that the upper bounds we construct being equal, and the fact that we can get solutions to, say, the primal problem from the dual? Okay, and this is just an example of min-cut being used in some machine learning applications, and how you can kind of switch between the min-cut and max flow formulations depending on which one you think is more convenient to solve. So here's a second perspective on LP duality, and this is going to be the one that we carry with us when we talk about duality in general beyond LPs. And it's very similar to what we did before, but it's different enough that it's worth working through. So we have minimize C transpose Y subject to my docam just shut itself down. Sorry about that. C transpose X subject to AX equals B, and GX being less than or equal to H. And here's a second way of looking at constructing upper bounds, very, very similar to what we did before. We can say that let's, again, put a variable u here and a variable v here that's non-negative in every component. And C transpose X is always going to be bigger than or equal to C transpose X plus U transpose AX minus B plus V transpose GX minus H. For any feasible X and V that's non-negative. Why is that true? Well, if X is feasible, AX is equal to B, so this part was just 0, right? And if X was feasible, this part was not, it was less than or equal to 0 in each component, and I took V to be bigger than or equal to 0 in each component. So when I multiply them together and add them up, the components, or take V transpose G minus X, this has to be smaller than or equal to 0. Right, so C transpose X is always going to be bigger than or equal to this. So this is a lower bound for any feasible X in V that's bigger than or equal to 0. And now let's just call the set of feasible X the feasible set C, so that I don't have to write it all out. So it's just the X that satisfy these two constraints, AX equals B and GX being less than or equal to H. So we certainly know that actually if we maximize over all feasible X, that That was not really what I wanted to say. So now if I minimize my criterion over the feasible set, this gives me the optimal value of my linear program. In component for every x, C transpose x is bigger than or equal to this thing, provided that V was non-positive. So certainly the optimal value when I minimize over the feasible sets, they're going to also obey the same order. That's supposed to be a min. Right? Because I have this being bigger than or equal to this for every feasible x and V that's non-negative. So I can't. So now I want to take the minimum over all x in the feasible set on both sides of this equation, and that's what I get right here. And this is the optimal value of my linear program. And I'm just saying that it's lower bounded by the optimal value of this other problem. It's actually also linear, right? So this almost gives us a helpful lower bound, but we're going to make one more relaxation. We're going to say that this is going to be bigger than or equal to the minimum over all x of the same criterion. So does everyone understand why this relationship is true? If I take away the constraint set, certainly I can get smaller in terms of the optimal value of this problem. The constraint set can only make that bigger. And now this thing is a function of u and v. We'll call this whole thing g of uv. And for any v that's non-negative, this actually serves as a lower bound for the optimal value of our primal linear program. So let's just figure out what GUV is explicitly. I'm minimizing over all x C transpose x plus U transpose AX minus B plus V transpose GX minus H. So I'll just rearrange the terms quickly. So I get C plus A transpose U plus G transpose V transpose X minus B transpose U minus H transpose V. So what's the minimum value of this problem? I want to make that as small as possible. There's only two cases you have to think about. So U and V, let's just think about fixing them. I'm taking the minimum over x. What's the smallest I can make this? Yeah, it's minus infinity. Exactly. So this is going to be, so what happens first if it's multiplied by a zero vector? Then it's just going to be minus B transpose U minus H transpose V. If we happen to pick U and V such that we multiply x by a zero vector, which means that C is equal to minus A transpose U minus G transpose V. Otherwise, it's minus infinity. Right? Because if this had any component that wasn't zero, we just would take x to be the opposite sign of that in that component, and larger and larger and larger. There's no constraints on x, and we get a minus infinity, which is the best we can do from the perspective of minimizing it. So the lower bound we construct, this is GUV. It's going to be minus infinity if we have U and V that do not satisfy this linear constraint. Otherwise, it's going to be equal to minus B transpose U plus minus H transpose V. So to get the tightest lower bound possible, we're going to maximize over all V that's bigger than or equal to 0 of GUV, which is the same thing as maximizing minus B transpose minus H transpose V, subject to the constraint that, right, it's not minus infinity, because that's not going to be good from the perspective of maximization. C equals minus A transpose U minus G transpose V, and V being bigger than or equal to 0. Okay, so look back at what we had before. This was the exact same dual LP we derived with our slightly different construction. So why do we prefer this construction, where we actually start by lower bounding the objective pointwise on X and then take a minimum over the feasible set? It's because this construction we can carry forward to general problems beyond linear programs. So what we just did in these few lines here is completely general, and we can apply it to actually any convex problem, not just linear programs, to get its dual. So let's take a break, and when we come back, we'll talk about that general form. First half about what happens when we can't make it so that we get like the dual variables to add up to the primal constraint. So another way of asking, of voicing that same concern, is what happens when we can't find U and V such that minus A transpose U minus G transpose V is C? What happens if there are no U and V that satisfy that linear equation? Then what's the dual problem now? What's the optimum of the dual problem? It's just minus infinity, right? Because it's not feasible. So the maximum of like the empty set, we kind of take by convention to be minus infinity. We have no better lower bound for the primal than just minus infinity. So here's the rest of today, which now is like short rest of today, but we'll probably have to talk about this next time as well. So let's go to the very general setting now. I went from the simplest setting to the most general setting, but the nice thing about duality is that it's just the same steps now that we did with linear programs. And it's a sequence of very simple steps that may appear like they're getting us nowhere, but they actually lead to some very powerful equivalences between problems. So we're going to take this general framework, minimize f of x subject to a bunch of inequality constraints, which I'm calling hi being less than or equal to 0, and then a bunch of linear equality constraints, which I'm calling Lx being equal to 0, or for j equals 1 through r, and for I equals 1 through m. Actually, at this point, I take that back. We're not going to even presume that this problem is convex. So f need not be convex, the h's need not be convex, and the lj's need not be affine or linear. They can just be arbitrary functions as well. Of course, we're going to pay special attention to the convex case because we're going to say a little more in that case. But at least for now, we're going to be completely general. And we're going to form this thing called Lagrangian. And it's just going to involve introducing a bunch of variables where I put u's here and I put v's here. So ui's and vi's. And my ui's need to be bigger than or equal to 0. And the Lagrangian now is a function of 3 variables, L, x, and u. L is a function of x, u, and v. And all I do is I take my criterion and I add to it 2 terms that have to do with the 2 constraints that I have on the optimization problem. The first is ui times hi of x, and the second is vi or vj times lj of x. And what do we know? We know that if x is feasible, then I claim that f of x is bigger than or equal to L x uv. Actually, one more thing. I need v to be each vj, or each ui to be bigger than or equal to 0. Why? Well, because if x is feasible, then hi of x is less than or equal to 0. So if I multiply by something bigger than or equal to 0, then this whole thing is less than or equal to 0. And if x is feasible, then Lj is 0. So I can multiply it by whatever I want, and this whole term is 0. So I get something less than or equal to 0, something equal to 0, and I add to that f of x. So it certainly has to be less than or equal to f of x. Right, so it's a very simple argument. So what have I done here? I took this example from your textbook, and the solid line is our function f. And the feasible set here is x between about minus 0.5 and 0.5, a little bit in from that. And then I took the Lagrangian, I formed the Lagrangian of this function, which is just written up there, right, or written on the yellow paper. And I looked at it for different choices of u being positive and v. And so you can see that as I vary u and v, this is what I get. I get different lower bounds. Oh, sorry. I'm sorry. These dotted lines up here are different Lagrangian functions over x for different choices of u and v. And you can see that within the feasible set, they are all smaller than or equal to f of x. As long as x is feasible, any one of these lower bound functions that I compute, Lx fixing some u and v, is less than or equal to f of x. That doesn't hold true outside of the feasible set. That's pretty obviously true. Why it doesn't hold true is because outside of the feasible set, this guy might have the wrong sign, and this guy won't be equal to 0, so there's no reason that bound should hold. So what do we do after this? Well, we form what's called the Lagrange dual function. And remember, we had this sequence of arguments that said that the optimal value of the primal problem, which we'll call f star, is equal to the minimum over x in, we'll call the feasible set C again, of f of x. And because I know that f of x is bigger than or equal to L of x uv for every u and v where u is non-negative and x is feasible, I can certainly write that as bigger than or equal to minimum over all feasible x of L of x uv, provided u is bigger than or equal to 0. So if we could write down this as a function of u and v, this whole thing, that would be a lower bound. But this isn't easy, minimizing over this constraint set. Analytically, it's usually not easy to do this, or it's actually usually not possible to do this if the constraint set is anything but trivial. So we form one more inequality where we say that this is bigger than or equal to if we had no constraints on x, and I still minimized L of x uv. Again, provided that u is bigger than or equal to 0. Right, because if I take away the constraints, I can only make the minimum of that problem smaller. And I define this to be some other function g, which is only a function of u and v. So I've minimized out over x. And so now the optimal value of my criterion is bigger than or equal to this function guv, as long as u is non-negative. So here's another example. Right, so this is an example where I actually only have one constraint, and it's an inequality constraint. And this dotted line is the optimal value of my problem. In fact, this is the same example as previously, I believe. But I'm just now showing you the optimal value of the primal problem in a dotted line. This is f star. And this is now g of just one variable. It's just g of u, because I didn't have an equality constraint, so I had no v. And you can see that for any value of u, here it's called lambda in the plot, that's non-negative, this function lies below f star. That's just this relationship. G u v is always less than or equal to f star for all points u that have the property that they're just bigger than or equal to 0. So how would we find the best lower bound for our primal problem? Well, from the picture it's obvious, and so it is from the math too. We would just maximize GUV over all u and v such that u is non-negative. That gives us a lower bound for our primal problem. And what can we already see from this picture is that in this case, when we did that, what would we get for the lower bound? We get this point up here, which is actually not equal to the primal optimal value. So here's an example for a quadratic problem. You can see what it looks like. We talked about LPs. Here's a QP example. So I have now 1/2 x transpose qx plus c transpose x subject to ax equals b, and x being bigger than or equal to 0. So I guess the words quadratic program, now that I'm saying them out loud, are probably something that you are not totally familiar with because we have not introduced that yet. But a QP is just a linear program where we make the objective quadratic. It's the only difference. And we'll talk about them in some detail. Barnabas will cover them in a bit. It's a step up from an LP. So let's form the Lagrangian now. Just treat it like a generic problem because we know how to do it for generic problems now. L of x, u, and v. So I'll put u here, which has to be bigger than or equal to 0. And I'll put v here, which is unconstrained. And I'll write this as minus x is less than or equal to 0 to fit the standard form of the problem. So that's just going to be 1/2 x transpose qx plus c transpose x minus u transpose x plus v transpose ax minus b. And let's minimize this over x to get the Lagrange dual function. So remember, GUV is the minimum over all x, not just feasible x, but unconstrained, of L of XUV. So how do we do that? Well, in this case, we can do it analytically. I just get 1/2 x transpose qx plus c minus u plus a transpose v transpose x minus b transpose v. C transpose x minus u transpose x, v transpose a transpose x, b transpose ax, yeah. So what's the minimum of this problem? I'll give you a hint. Go back to the case where it's just univariate, ax squared plus bx plus c. Just think about that, and the same is true for the matrix world. So what's the value of x I would stick in to get the minimum first?
Q inverse C minus U plus A transpose B.
Yeah, it'd actually be
What's D transpose somewhere?
minus that, yeah. Right, so it's just minus, so okay, in this world, I think I said this already once before, it's minus b over 2a. Just take it from getting the derivative and setting equal to 0. It's the same thing here. Minus b, and then over 2a, but I can't divide by a matrix. It's just minus q inverse b. So I plug that in, and I get that GUV is equal to, I get, well, let's just do it. 1/2 minus q inverse c minus u plus a transpose v times, or this transpose q times itself, c minus u transpose plus a transpose v, plus minus c minus u plus a transpose v transpose itself, or sorry, q inverse is minus c minus u plus a transpose v. That was this transpose x minus b transpose v. So here I have 2 minus signs and a half. So I get just a half of this quantity. And here I have no negative sign there. 1 of that quantity. So I get the whole thing is just minus 1/2 times c minus u plus a transpose v transpose q inverse c minus u plus a transpose v minus b transpose v. So that's my GUV function. It is also a quadratic in u and v. And what do we know? We know that for any value of v and any value of u that's non-negative in each coordinate, this is going to be a lower bound on the primal optimum value. Oops. Okay, so that's a pretty non-trivial fact for this quadratic program. And you can do the same thing if q is not invertible. So we assume q is invertible here, but we can also get an explicit dual function in the kind of degenerate q case as well. So here's a picture of that. I took a quadratic program in just 2 variables now. And I just had no equality constraints, but subject to the constraint that each component of x had to be non-negative. And here is the primal quadratic objective. And I formed the dual objective just like this. It's also a quadratic. And look, I have minus sign, so it's going to be tilted downwards here. And I also have the constraint for this that it has to also be non-negative in both of its coordinates, which were u, right? Just like I had here, I had this. This was a valid bound for any v and u that's non-negative. And so here's my primal quadratic objective. Here's the dual function. It's also quadratic. And it turns out that the lower bound we get from the dual function, if we look at the best lower bound we can get, it's equal to exactly the minimum of the primal objective. So in this case, we did get that our lower bound from the dual problem is exactly the same thing as the optimal primal criterion value. So now we've seen it true for LPs and for QPs. We saw it not true for this weird function I drew here. Okay, so we're out of time, but next time we're going to talk about when that's true in general. Why doesn't somebody give me a guess? What problems are we going to be able to say that we actually get what's called strong duality, where the dual and the primals are equal? So it wasn't true for this, but it was true for QPs and LPs. Convex. It's basically the answer is most convex problems, right? This is not convex.